Hello everyone, welcome to the first episode of Research at IIT Delhi. Today we have amongst us Professor Adarsh Barik. He's a professor of computer science and he has his research specializes in optimization of machine learning. So would you please introduce yourself?
Yeah, hi. So my name is Adarsh. First of all, it's great to be here and be part of this interview. Right, so I joined IIT Delhi pretty recently, like 4 months back, and I work in basically optimization for machine learning problems. I'll try to explain. So this is an age of LLMs, right? So LLMs are nothing but machine learning models. Now we make many claims about LLMs. We say that these LLMs they work with very high accuracy. What we are trying to say is if I ask some question to LLM, then it will give an answer which will be very close to the correct answer. But my research group asked the question, how close is this close to correctness, right? And what is the accuracy? Like how many times would you get the correct answer? More than that, any machine learning models, including LLMs, they'll need some data to train on. So my research group would ask the questions like how many data points are needed for training this big machine learning models, right? So these sort of theoretical questions about the machine learning problems. So I try to quantify the performance of machine learning algorithms and try to see how fast would they work, how many data points would they need for them to perform better. So those sort of questions. Yeah.
So would you like to tell us about some specific projects you have worked in the past or you are working now?
Yes, so currently I'm focusing on problems of sequential decision making under uncertainty. Let me try to give an example. So suppose you go to a share market and you want to invest some money in the share market and you have multiple stock as options, right?
Yes.
So you have 4 options and you want to invest your money on these 4 stocks. Now, before knowing anything about the future, it will be if I put all my money in one of the stock, then that won't be a good decision to make. A better decision would be to put some money in each of the stock, wait for a month, and then get a feedback from the market and try to adjust my decision based on the feedback. So this is called sequential decision making based on the feedback. But you don't know the feedback, you don't know the future. So you are taking decision without knowing the future outcome in the hope that in overall the run of your investment you will do good against some sort of baseline. Okay? I try to find algorithms which do well in these settings with provable guarantees, right? Now there are some challenges in this sort of setup. One of the challenges would be what happens when some of the feedback that you are getting from the market is not correct. So the market tells you that invest on this particular stock, but there is some market manipulation going on by some agent who doesn't want you to succeed in this investment strategy, right? So now I try to develop robust algorithms against this sort of corruption. So my algorithms, they can take into these corrupted feedback and try to work through them, try to minimize the effect of these sort of corruption. So that's one of the projects that I've been working on currently. In the past, I have worked a lot on something called invex losses, right?
Yes.
So you might have heard about convex and non-convex losses. Let me just for the viewers, I'll just explain very briefly. So convex losses are the losses which are easier to deal with. When we say that we can easily minimize some sort of loss, then more often than not we are talking about convex loss. And when we say that this loss is difficult to minimize, that like you might have heard that LLMs, the training for LLMs is very difficult, right?
Yes.
So these loss functions for these LLMs, these are non-convex in nature, so they are difficult to minimize. Now my work was trying to find a balance between convexity and non-convexity. So meaning we were trying to find a class of non-convex losses, this difficult to minimize loss functions, which are still tractable. And this class
which are somewhat like convex losses.
Somewhat similar to convex losses, so which have the property of convex losses, but they are actually non-convex in nature.
Got it.
Yeah, and those were the invex loss functions, and my work in my previous works, I have dealt with these sort of invex losses and how to develop strategies to minimize them. Yeah.
So how do you see your research like making an impact in the future?
Right. So I'll give you an example. Again, I'll come back to this example over and over again, which is the training of LLMs, right?
Yes.
So few years back, we don't have to go too far. In 2013, there was this, or 2015, I might be misremembering the year. There was this well-celebrated training algorithm that people came up with for training the neural networks. Everybody was excited, It used to work really well in the practice, and even now people use that algorithm to train the neural networks. 3 years down the line, some researchers came together and they proved that this algorithm that people are celebrating, it does not even converge. So meaning it, for some problems it might even give you extremely bad results.
Yes.
It took some researchers to carefully analyze the algorithms, to develop some sort of mathematical guarantees for the performance of algorithm, and that's why they said to the general public that this algorithm might fail in some problem instances. So my work focuses on these sort of problems.
Mathematical.
Yes, my work tries to provide mathematical guarantees for the algorithms, for machine learning algorithms or optimization algorithms in general. And in practice, these are important because yes, you might feel good about your LLMs working now, but what happens in the future? What happens when data changes? What happens when you don't have enough data to train your model on? So these sort of questions require very precise mathematical answers, and my research tries to give those answers.
Okay, sir. That's actually quite amazing. So I would like to ask that real world data, as you talk, it has a lot of noise, and when we have these sensors, they just don't capture the data; they also capture the noise. So how your research focuses on just minimizing the noise, because it's quite important for us to actually get only the data which is important.
Yes. So the problem is this, right? You have this noisy data or corrupted data, and if you try to make prediction based on this corrupted data, then your prediction might be wrong. So the problem here is you can't do much about collecting these corrupted data, because if sensor is not working, there is not much you can do unless you figure out that this particular sensor is not working and you replace that. But if you don't have that capacity, then you collect all the data from the sensors, be it corrupted, be it not corrupted, and try to make some prediction based on this data which might be corrupted. So I try to develop robust algorithms which can deal with this corruption. Now it's a difficult problem. It's a difficult problem as it is. Collecting sensor data and giving a meaningful prediction out of this data is already complicated problem. On top of that, you add this extra complexity layer where you are saying that some of the data set might be corrupted. So how do you deal with that corruption? So my work develops strategies to minimize the impact of this corruption, and so that we can still predict some, we can still make some good predictions.
Yes.
Yeah.
So how does your data does it? Like what are your mathematical? Like you provide mathematical theoretical models for it.
Yes. So one way of doing this would be, again, to make your prediction iteratively. Right? I'll explain what I'm trying to say. So suppose you have say 100 data points and 90 of them are good, 10 of them are corrupted. But you don't know which 10 of them are corrupted. So what you do is you take say 90 out of 100 at random. It could include some of the corrupted data sets, and you try to make prediction based on.
So we basically know this thing that 90 of them are good.
Yes.
This data we have.
Yes. So you have some proportion which is corrupted. You know that this corruption proportion cannot exceed a certain level. So you take this 90 samples, it might include some of the corrupted samples, you try to make a prediction based on that. Now you want, and in the second step you update your ML model parameter of your machine learning model, and now you see if I take another set of 90 samples, is my accuracy improving? If it is improving, then you discard the first 90 samples, you work with the other 90 samples which are giving you the accurate prediction, right? You keep on doing this iteratively, and we show that you don't have to do it say infinite amount of time. Within a finite number of iterations, you'll be able to figure out
the correct 90.
No, you might not be able to figure out the correct 90 samples or the uncorrupted 90 samples, but you will be able to figure out 90 samples which give you good prediction.
So you might have some noise.
Even if you have some corruption in this set of 90 samples, they don't impact your prediction that much.
So because the number is quite less.
Yeah, and you have done this iteratively. So extremely corrupted samples which were making your prediction go wrong, you have already discarded them. So whatever corruption there is in your sample is not big enough to impact the prediction.
So sir, like a huge problem in AI today is that we have black boxes. Like we know they work, but we can't prove why. And your focus on like provably correct all algorithms which provide mathematical evidence for how much data a model needs and when it will succeed. In fields like healthcare or finance, it usually it's not good enough. Like we need a good amount of prediction of a data set. So how does your work on provably correct algorithms guarantees for things like sample complexity help build the level of trust which we need to use AI in this high stakes or life or death situations? Because as we talked about stocks or like healthcare, these are areas where we need very fine, very accurate data.
Yeah. So this brings us to something called concept of sample complexity, right?
Yes.
So if you want to say that my ML algorithm works or my ML strategy works, then you need certain number of samples. Now there are two fundamental limits. So your ML algorithms would need a sufficient number of samples to do good in the data set. And if you don't have that sufficient number of samples, then there is no guarantee then that it will work well in the data set. Now the second limit, fundamental limit, is necessary number of samples, which tells you that if you don't give me this necessary number of samples for this particular ML task, then whatever you do, whatever algorithm that you use, you can't do anything about the problem. So we need to figure out these fundamental limits. We need both necessary number of samples and sufficient number of samples.
Yes.
To give you an example, suppose you want to deploy an ML model in some healthcare sector, right, where accuracy is extremely important to you.
Yes.
Now somebody tells you that this is my perfect ML model, but I trained this ML model with say 5 data points, just 5 data points. Would you expect that model to work in the real world data?
No.
Probably not, right? 5 is a very small sample
Yes.
size. So you want some reasonable number of samples, but what is that reasonable number of samples?
Depends on.
Yes, so depend on the problem, depends on the algorithm that you're coming up with. So my work deals with establishing these fundamental limits on sample complexity for a particular ML task or for a particular ML algorithm. Yeah, and it's extremely important because you don't want to keep your health in the hand of some algorithm which has not been proven to work in.
How much variable should be there for a particular data set? Yes. Okay. Also, sir, as you have told that corrupted data have always find new ways to trick AI. So, do you think your mathematical problem or your mathematical shield or the mathematical solutions you provide can stay ahead of the corrupted data or the noise which are captured in electronic devices for different purposes?
Yeah, so this is a complicated problem, right? Now, if there is an adversarial agent, they'll keep on trying to corrupt the feedback or the data that you're getting. Now, it's extremely difficult to filter out the corruption. What you can do is you can take this corruption into your data set, but you should try to make robust prediction, which minimize the impact of this corruption. So the work I do tries to do that. We are not trying to filter out the corruption because it's difficult to do that. Yeah, but we are trying to minimize the impact of these corruption. So hacker might still try to infuse some corruption in the data set, but I want to develop robust enough algorithms which can deal with this corruption and still provide some robust results.
Amazing. So, you have worked on mathematical problems that are normally difficult combinatorial for computers to solve. How does your method make this problem simple enough to run on basic hardware?
Yeah, so one problem with the say combinatorial problems is the search space becomes very large.
Yes.
So if you want to search for the solution one by one, then in your lifetime it won't be possible. One way of dealing with this sort of problem is to make approximations, right? So now you are not dealing with this huge or is this big search space, but you are trying to say that I'll make some approximation and I'll try to reduce the search space. Now the other way is to relax the problem, relax the combinatorial problem. And it has been seen that once you go from say discrete combinatorial setting to a continuous setting, you can do better in terms of say optimization. So I try to model this combinatorial problem or relax this combinatorial problem in continuous regime and then try to solve the problem there. But as soon as you make some relaxation or some approximation, your solution quality would degrade.
Yes.
Right? So my job here is what are the technical conditions that you can impose on the problem such that we can prove that the solution to this relaxed version of the problem or continuous problem which is
approximately correct.
Either approximately correct or exactly correct, exactly matches with this combinatorial problem. So those sort of relationship between a relaxation and this difficult problem. It does require some technical conditions. Without technical conditions, these are impossible problem to solve. So we come up with this good.
Can you give an example of this?
Yeah, so one of the thing that I worked on is trying to figure out the structure of, say, something called Bayesian networks. So you have a system where a lot of variables are there, and these variables are trying to interact with each other. And now, based on the data coming from the system, you're trying to capture this interaction. So this interaction, you can model it as a graph.
Okay,
And
yes,
you want to
yes,
learn
yes.
the structure of this graph from the data set that you're getting. Now, in general, if I tell you this problem, or if I ask you to solve this problem, then this is something called NP hard, which are difficult problem to solve in general. But now if you make some approximations here, if you make some assumptions here, one of the assumptions that we came up with is by saying that the interaction between say these variables in the system, that is limited to a very specific kind of interactions, right? So you can have, say, many different sort of interactions, but we are focusing our work on this small set, which does not capture everything, but it captures good enough number of interactions. Now with this extra assumption, can you learn the structure? And we showed that yeah, you can do that, and you can do that in polynomial time, which is a good result.
Yes, that's quite impressive, sir. Thank you so much, sir. It was really nice having you here for the interview.
Yeah, thank you.